So far in this chapter, we have looked at an introduction to fatty acids. Now we're going to look at our first lipid, triglycerides. We'll look at the structure and we'll also look at a reaction that it can go through. So we've seen some of the basic foundation blocks of building, that's a fatty acid, and now we're going to look at one of our lipids that contain esters, the triglyceride. So I'm going to give you an even simpler version than this of a triglyceride. We call this a block diagram sometimes. And so a triglyceride is made out of a glycerol molecule, and you might recognize that all tells me, hey, this is going to be an alcohol. And then that glycerol is connected to tri. The tri is going to be 3 fatty acids. And again, this is not the exact shape, but it gives us kind of a cartoon, simple way to think about these structures. So a triglyceride is just a glycerol plus 3 fatty acids. And we will see that they are linked with esters. And overall, as I look at this, I can see there's a lot of carbons and hydrogens and no OHs. So these are going to be nonpolar. And if you have butter or vegetable oil or margarine or any of those things at home, that's what these are. That's what triglycerides are. This is how plants store their carbon energy, and how humans also store our carbon energy is as triglycerides. So this is a storage molecule. As I look at this triglyceride, you should be wondering at this point, where's the functional group? And hopefully you found some heteroatoms, some oxygens. Find a carbonyl and look for its neighbor, the oxygen. And so I can see here that we have esters that are linking those 3 fatty acids to the glycerol backbone. So that is a triglyceride. Let's talk about how we might see some implications of melting points with this. So these are actually really short carbon chains for a fatty acid. They go up to like 18 sometimes even. So let's take a look at these tails here. And let's just make some connections that go back to some of our older chapters as well. So if I have fatty acids here with more cis double bonds, here I don't see any cis double bonds, right? But we saw some cis double bonds. I could have tails that looked like this instead, like these omega cis ones earlier. So if I have more cis double bonds or less carbons, then if I can remember cis double bonds and less carbons, that means that I have weaker attractions between molecules or weaker IMFs. If I have weak IMFs, then I also have low melting points, relatively, and boiling points. So relatively low melting points. And what that means, if I go to my kitchen and I'm looking for one of these, I could say that if they have those low melting points, that means that they are liquids at room temperature, not solids. Solids would have not cis bonds and would have more carbons and strong IMFs and high melting points, and then you would get a solid instead. So how these tails look is going to have a big impact on those physical properties of your compounds. Liquids at room temperature we call here oils. It's more of a nutrition word, and if it's a solid at room temperature, we would call those fats. And those tend to be, plants tend to give me my oils. Coconut oil is an exception that is actually not having cis double bonds, but it's got a few carbons, small amount of carbons. And then animals are who are going to give you generally your fats or your solid triglycerides. So that's a melting point, boiling point kind of thing to think about. The next thing we're going to do on this page is look at what kind of reaction this triglyceride could go through. And if we want to digest it, then digestion, the first step is going to be hydrolysis. We've seen that before. You add water and you break something. So to this, I would add 3 waters, and I would probably have some acid, like stomach acid, and then also lipase enzymes. Those are lipid breaking enzymes. So if you can think back to hydrolysis, we were going to come in and we were going to slice our esters, and we're going to do it 3 times here. I have 3 different esters to slice. On the carbonyl side, I always add the OH, and on the oxygen side, I add an H. So we'll see those added on in a minute. I just have to do it over and over and over again. So when I break these, let's just start at the top here, okay? So I have C with 2 H's that are already there. And then I connect over to an oxygen, and that's where my hydrogen is going to get added on. So this is the hydrogen that I'm adding to that broken oxygen. Notice this is still connected down, all right? So I'm just going to copy all the way down. These bonds are all still intact, and each of these is connected to an oxygen. And then each of these, because I have 3 waters, would get a donation of a hydrogen. And this compound that I just drew is called glycerol. All right, now looking at these others here, this would be, if I look on the fatty acid side, I have a carbonyl, and I'm going to condense this down and say that I have CH2, 1, 2, 3, 4 times, and then a CH3 at the end. And that needs something where this bond has been broken, right? When you break a bond, you got to replace it. So I'm going to put the oxygen first, because the oxygen is what's connected to the carbon, and then an H. So this is now a carboxylic acid, right? Can you see that? It's just written backwards. That's going to happen over and over again, and these are all actually identical. So every single one of them has those 4 CH2s and the carbonyl, and every single one of them is going to take its part of a water molecule. And so what I ended up with here, and I would put a plus here because these are separate molecules, right? What I ended up with is 3 fatty acids. So when you eat any kind of oil or fat, any triglyceride, then your body is going to, one at a time, it doesn't do this all at once usually, but it'll lyse off 1 fatty acid and a second one and a third one. And so then you have this, and you can go metabolize these in different ways. Now, let's say you want to store some of that fat, right? Because our bodies think that a famine is coming, always. And so they want to store fat if you have extra energy. Then we would do the reverse reaction. And the reverse reaction is called lipogenesis, or lipids and making. I'm not sure exactly what that root is, but lipids and beginning, or creating the lipids. And so we actually would reverse it, and this is what we would find in our adipose tissue. These are the triglycerides that we store so that we can break them down for carbons later on. So that is looking at the structure, thinking about the melting points, and then being able to do a hydrolysis of a triglyceride.